afternoon session on compilation. And our first presentation is from Nystrom. And I give him the word. Thanks, Nate.
Sorry. Okay. Hi, my name's Nate Nystrom. I'm from the University of Lugano. That's usually the English translation of the university I'm from. And in Switzerland. You are in Vancouver. Okay. So I want to talk about supercompilation. So this is something I've been working on for maybe about a year or two. And supercompilation is this idea by Valentin Turkin from the 60s and 70s. It was published first in English in 1986, previously in Russian. And the idea is kind of very simple. You basically just want to partially evaluate your programs as much as possible at compile time. And as you're partially evaluating, you monitor the progress of the evaluation to detect possible non-termination and possible repeated computation. And in the end, you produce a residual program which hopefully is faster. Okay, and this has lots of applications, in particular for program optimization, theorem proving it's used for, automatic function inversion, and there's many other applications. I'm basically interested in, well, the first one and the third one, in fact. And I'm going to talk about that today. Okay. So the nice thing about supercompilation is it subsumes many existing compiler optimizations, particularly for functional languages. So obviously constant propagation, that's an easy one. Inlining, but also deforestation, so removing kind of intermediate data structures. And there's been a lot of work on supercompilation in the functional languages community, in particular in the Haskell community, because of this potential to get great performance in the end. However, if you've all noticed, your Haskell compiler, for instance, or let alone your Scala compiler, doesn't actually have a supercompiler baked in, and this is because there are a lot of practical issues. One, supercompilation takes quite a long time to run, and two, you get a huge code explosion problem, right? So in the worst case, you know, this exponential code growth. And this basically leads us to, or leads me at least, to believe that we just need a better understanding of supercompilation to make more progress in this area. So, you know, it's been built for languages like Haskell. Supercompilers have been built, but they're just not yet practical enough for use, for daily use, right? Right, they're not going to replace -O anytime soon. Okay, so to better understand supercompilation, I decided I would write a supercompiler. And so I've developed a framework in Scala for building supercompilers. And the idea is somewhat similar in spirit to Max Bolingbroke and Simon Peyton-Jones's supercompilation by evaluation. What we're going to do is take an interpreter and extend it to turn it into a supercompiler. Okay. So the framework also contains some support for building supercompilers, not just for kind of pure functional languages like Haskell, but imperative languages, because that's more of what I'm interested in, kind of imperative and functional languages also. And we've used the framework to build a supercompiler for JavaScript. And I'll talk about that towards the end. Okay, so most of you probably do not know what supercompilation actually is, other than the one sentence I gave you earlier. So I want to step through an example just to explain what's involved, and then I will go back and talk about what our framework actually does for you. All right. So how do you start? Well, you start with an interpreter. I'm going to start with a really simple interpreter. Basically, you have an expression and a continuation. And to do evaluation with this interpreter, you just step from one state to another. So you have some focus expression with some continuation k, and you step to a new focus, a new state where you have a different expression and different continuation. Okay. This in the in the supercompilation literature, this is called driving. So when I say driving, I just mean evaluate, right? Okay. So here's a simple example. Here's map, or a version of map. I wrote it in Scala syntax because this is a Scala Symposium, but keep in mind our framework works with interpreters written in other languages, or any language you write an interpreter for that matter. Okay, so map takes a function argument, a first argument, and it takes a list and gives you a new list, right? And the way it works is you pattern match on this input list, AS. If it's nil, you get nil. If it's not nil, you apply the function to the first argument, and then you recurse on the rest. Okay, so I hope you all understand that. Okay. So, and what we're going to do is just supercompile this one expression. I want to map +1 over a list ZS. And what's important to know is that list, I don't actually know at compile time. I don't know the value of that list. It's just an abstract. It's just a variable, right? I don't actually know what the value is. So I can't actually compute the result directly, right? Okay. So we start in this state where the focus expression is this expression we want to supercompile, map +1 on Z's, and the continuation is empty. And if we drive, we get basically the body of this function where the arguments have been replaced by the parameters, right? So we're going to match on the input list Z's, and in the nil case, we return nil. In the other case, we add 1 to the first element and then recurse, passing in that function again. Okay. I should say I'm glossing over lots of details, but I just want to convey the idea rather than spend time in the details. Okay. Okay. So we have this state. Basically, we have this pattern match on Z's, and we have this empty continuation. How do we drive further from this state? Well, we can't. Right, we can't because we don't actually know the runtime value of Z's, right? So we do this pattern match, but we don't know which branch to take. So this is called a stuck state, and what we do is we split. Basically, we say, well, consider the case where Z's is nil, we're going to do something, and also consider the case where Z's is not nil, and we'll do something else. So this is called the split, okay? In the nil case, well, we change the focus to just nil, the body of that case arm, right? And the continuation, again, is still empty. And in the other case, we change the focus to the body of the other arm, and again, the continuation is empty. Okay. And what we're going to do with these two states is just recursively supercompile those and hopefully produce some residual program. Okay. So the first case is easy. It's just a value. The second case, we have to actually do something with. So I'll just consider the second case, right? So we have this state where we're doing b plus 1 appended to, prepended to, map plus 1 on BS and empty continuation. If we drive that state, we first have to evaluate b plus 1. And so we try to evaluate that, and that basically just makes the continuation get bigger, right? So so the continuation is just saying, after you evaluate b plus 1, prepend it to the result of doing map plus 1 on the rest of the list. Okay. And then you drive that, and you get just b. So to figure out what b plus 1 is, we have to figure out what b is. So you evaluate b, and then you get into this state where whatever the result of that would be, we add plus 1, and then you do the recursive map. Okay. So again, this is actually another stuck state, because I don't know what b is, right? I didn't know what ZS was, but I definitely don't know what the first element of the list is either, right? I don't know the contents of the list at compile time. So again, we're stuck. So what do we do here? Well, we would like to split, but we can't because there's no branch, right? You can't, just decide, oh, and it matches one of these two patterns, right? So what happens here is we do what's called a rebuild, and this is basically we convert b into what's called a residual state, and basically it just says leave this b alone and let it go into the output program. We can't do anything more with it. Okay. So I've denoted rebuild states as kind of this angle brackets around the value. Okay. And then we can just actually continue driving. We continue driving as if this rebuild value, this b in brackets, this residual b, is just a value like any other. So we drive that, and driving on rebuild states actually just consumes the continuation and builds a larger builds a larger residual expression. So if you have a residual b and then you want to do +1 on that, you get a residual b +1, and then that changes the continuation. And then to evaluate this continuation, you have to basically evaluate this map, and you end up in this state where you want to evaluate the map, and the continuation is prepending this residual b +1 to the list, to the result list. Okay. So now we're in this state. We have a map +1 on the tail, and we're going to prepend b +1. All right. So here, if you notice, this map +1 on BS is exactly the same as the original expression we wanted to supercompile in the first place, right? The original expression was map +1 on ZS. This is map +1 on BS. It's the same thing, just renamed. And the supercompiler is going to detect this case and say, hey, I'm basically going to go into a loop here. So let's fold. And what fold does is rather tricky, but what it does is it basically replaces that expression with a call to a function that will be filled in later, right? And actually what this function that to be filled in later will do is basically be a specialized version of map that adds 1 to every element of list. Okay. So we fold and we get this residual call to this new function map1, and we don't know what the body of that is because we haven't finished yet, but we will finish, actually in a few steps. Okay. And so we drive that state on that continuation, and basically we end up with this residual b +1 prepended to map1 of BS. Okay, and the empty continuation. Okay, so now driving actually is done. The continuation is empty, so you can't drive anymore. You can't. The continuation says what to do next. There's nothing to do next. You're done. Okay, but remember we were in this split state, right? Earlier we branched on whether ZS was nil or not. So we're back here, and if it was nil, well, basically we did nothing and we ended up with nil. And in the other case, we ended up with this residual b +1 map1. And what we have to do now is reassemble the split states back into one state. And basically you end up with this, right? So you pattern match on z's. If it's nil, you return nil. And if it's not nil, you do b +1 and recursively call map1. Okay. So this is actually the result of supercompiling that original expression. And so before, when we folded, we kind of introduced this function, map1, whose body we didn't know yet. Well, this is the body, right? So what we do is we just say, oh, well, let's slap a name on it. Let's call it map1, give it a parameter name, and we rewrite that original expression as a call to map1, right? So now we're done supercompiling. We've rewritten this call to map, basically specializing it on the first argument. Okay. And this, by the way, is why you get lots of code bloat, because basically I've duplicated map, right? And so, in general, for instance, if you call map lots of times, as you do, you may end up with hundreds and hundreds and hundreds of versions of map. Okay. So this is basically what supercompilation does, right? It ends up specializing functions. Okay. So to use our framework, what do you have to write? Well, you have to write an interpreter. You have to write something to do the splitting. You have to write something to do the rebuilding. You have to write fold. And you have to write what's called a whistle, which I'll get to later. Okay, so let's take these one by one. First, the interpreter, well, you just start with a normal interpreter. It's actually a partial interpreter, so you don't actually have to finish writing your interpreter. You can just return none when you don't know what to do. You can implement this interpreter in any way, really. You can use term rewriting or an abstract machine as long as it's implementable with a step function. The framework actually gives you a interpreter for a simple imperative language. And actually, we've used this simple imperative language. We've extended it to support JavaScript. And we've done this without actually implementing all of JavaScript, because in the worst case, because if you don't know what to do in JavaScript is actually a very complicated language. So for the tricky cases, we just return none. We don't know what to do. And what happens is the step function gets stuck and you split. Okay. So, and actually in the very worst case, in general, you can just always return none, which just means you have a very slow identity function on programs. But stuck states are punted to splitting. So what does splitting do? Given a stuck state, you have to return a list of states to drive. You basically have to break this state up into multiple states. So for instance, if you're stuck on E1 plus E2, you would return 2 states, one that evaluates E1, one that returns E2, and then you also return, split also returns what's called an unsplitter, which tries to reassemble the split states back into one, right? So you evaluate E1 to E1 prime, you evaluate E2 to E2 prime, and then the unsplitter is going to reassemble that into E1 prime plus E2 prime. Okay. The big problem here actually is that if the language you're writing an interpreter for is not pure, you have to evaluate E2 in the state produced by evaluating E1 because E1 might have had effects that you need to capture. And this actually is going to turn out to kill us in the end, unfortunately. So we'll get to that in a bit. Okay. When you're done splitting, you have to reassemble, and so we reassemble with what's called an unsplitter. This is just a function from lists of states. So actually, it's a function that takes, say you split into two states. It's going to take a list of length 2 of 2 histories of states, right? So it takes 2 states, it takes 2 state histories, basically all the states you went through since the split, and tries to reassemble some sort of state from that. Generally, you just look at the last state in the history, but or typically you look at the last state in the history, but generally you may have to look at other states to get a good reassembly. Okay. So either the unsplitting can succeed, it can fail, or it can actually just say try again. And we use this for conditional branches sometimes. So if you're doing this if your interpreter has continuations, sometimes you may get stuck at the end. And if your continuation was just a little bit longer, you can actually make progress. So we have this option to resplit, to just try again with a different set of states. Okay. Now, if reassembly fails, what happens is we rebuild, and this is turning an active state into a residual state. So, for instance, if you have x plus 1 as the state you're trying to deal with, this will turn into residual x plus 1 that you leave in the output program, and then basically you continue driving as if this were a value. It's not really so simple, it turns out, because you'd want to avoid work duplication. So x plus 1 would actually, you have to actually introduce variables to do this correctly without duplicating work. And you can't just treat x plus 1 residual as a value in general, but you can treat residual variables as values, and that works. Okay. But again, I'm oversimplifying in a few ways. So rebuilding is implemented with this function called rollback, which takes a history of states since the last split and rebuilds, usually just rebuilds the last state, but in some cases you need the entire history to do a rebuild correctly. So we give you the entire history. Okay. And for instance, if you have a free abstract memory location in that last state, you may have to back up a few states so that you actually turn that back into a variable access or something like that. Okay. All right. Once you have residual states, you need to drive them. Again, this just basically just grows the residual expression, and that's basically, so you just do driving on the residual states. Okay, so you have to extend the interpreter to handle that case. Next, you have to write a fold function. What a fold function does is takes, again, a list of states, the history of states you've been through, and gives you a new history of states. The implementation of this depends on how you actually implement the interpreter. So we allow you to implement interpreters in lots of different ways, but unfortunately that means The fold actually depends a lot on how you implement the interpreter, so it can get complicated. So the framework doesn't do the fold itself. It just gives you some utility functions to help you write a fold to yourself. For our JavaScript supercompiler, we do, as I said, we introduce this function stub and then replace the current state with the residual call to that function. And then when driving, splitting, rebuilding, it's all complete, you have the body of that function to drop in. Okay. One more thing is all this might not terminate. So you need this extra thing called the whistle. And the whistle is the standard name in the supercompiler literature. And the idea is when the whistle blows, you stop. Right. So the whistle is there to detect non-termination. 1 minute. OK. So whistles, there's a lot of theory behind whistles. But we choose one and give you that one. OK. So we give you a interpreter for an imperative language from which we derive a supercompiler for that imperative language. The main challenge in this is actually modeling the heap. And then we've used this kind of abstract interpreter supercompiler for generic imperative language to build a more concrete supercompiler for JavaScript. As I said, we don't actually implement all of JavaScript, not even the good parts. But again, the parts you don't actually implement, that just makes the step function get stuck and you're forced to split or rebuild. Okay. Compilation times are not that great, I will say, but not too terrible either. So it kind of depends on what kind of whistle you're using. So if you have no whistle, this is just a set of JavaScript benchmarks. If you have no whistle, it runs in less than a second. If you do have a whistle, a simple whistle, which just says, oh, if you go through more than 100 states, stop. That's a very simple whistle. A very simple way to detect non-termination. Just stop after 100 steps. That actually runs faster than if you have no whistle at all, because it stops earlier in some cases. And then we implemented this, what's called a tag bag whistle. And this is more precise, but also more slow. OK. Runtimes are, for the JavaScript interpreter, I admit, are not great. And I will not give you numbers. But this leads me to future work, which is, it turns out our approach for imperative language doesn't work very well. And the main problem is the heap, right? Every time you have an unknown function, the heap has to be sanitized. So what we're doing is we're starting basically, not from scratch, but we're starting work on building a supercompiler on top of an abstract interpreter. So for the JavaScript implementation, we're looking at JSAI, which is an abstract interpreter, which had pretty good results. This idea is actually suggested by Neil Jones of partial evaluation fame in a talk years ago. So this is the main thing we're focusing on, which is using an abstract interpreter rather than kind of a naive interpreter for JavaScript as the basis. So that you get a more precise model of the heap and you can make better progress. So we're experimenting also with different supercompilation algorithms, and you can read that. There's some related work. So there is actually another framework for Scala for supercompilation. This is focused completely differently. So we're focused on program optimization. This is focused on basically experimenting with different kinds of supercompilation. And it operates on process graphs, and it's a completely different way. And again, we're kind of based on this supercompilation by evaluation idea. OK, so that's it. The supercompiler framework SCSE is it's on GitHub if you want to play with it, or you can ask me questions, and that's all I have to say. Any questions?
So what's the difference between this and systems like the Grail compiler for Java they've been working on, or Python? Are they sort of similar techniques?
Yeah, so Grail and PyPy, yeah, they're based on partial evaluation, which is, I guess I would describe supercompilation as sort of partial evaluation on steroids in a way. it tries a lot harder. Supercompilation generally tries a lot harder to evaluate the program. So partial evaluators in general don't do this splitting. I guess that's the main difference. And they also don't tend to have the code bullet problems that supercompilation has either, or the runtime problems. They have some runtime problems, but not as bad. I think you could, in theory, you could take something like a supercompiler and plug it into, in theory, plug it into Graal and get some performance out of that. Yeah. Actually, I think, by the way, I think that the guy, one of the people who wrote this second Scala framework years ago, I think he actually works at Facebook, so you can go talk to him. Anyway.
Hi.
Hi.
Can supercompilation discover typical compiler optimizations like common sub-expression elimination?
It should, right? I guess it depends on how you model the state. I haven't actually looked at whether it can do some common sub-expression elimination. I'm not actually sure. Well, if you read the original Turkin paper, yes, because he makes sort of very grand claims over what it can do, right? But it's all in the, actually, you have to implement those, right? So in theory, it can do things, right? So I would say, and if one other use of supercompilation is you can plug it in, you can actually use it as a theorem prover. So if you want to prove that this expression and this other expression are equivalent, for instance, you just say, are they equal? And if it supercompiles to true, then you have a theorem prover there. And so you could actually plug that into your optimizer also and maybe get some benefit there. Yeah. Any other questions? There was one, okay. There was one there.
So I just had a question about this compilation times table that you had.
Yeah.
So if I understood correctly, this none whistle means that there's no whistle being called ever.
There's no whistle being, yeah, there's no whistle being called ever. The whistle is disabled. So in practice, this can mean basically the supercompiler will run forever, right? It turns out on these benchmarks, it doesn't. So that's why we can say it doesn't. Right, but basically here, so what the whistle does is every step you go through, it says, basically, have I seen something like this before, right? And says, and basically what it's trying to do is figure out, is something growing, right? So the really simple history equals 100 whistle just says, well, after 100 steps, if you haven't terminated, stop. The tag bag whistle is much more elaborate, but basically it traverses the entire state data structures, basically the entire history, traverses the state data structure and says, essentially, is the implementation of is the data structure for this state using the same classes as the data structure for a previous state, and also is larger. And this actually seems to work well. This is basically the whistle used in the Haskell, the GHC supercompiler. But I would say our implementation isn't terribly fast at the moment. But
thanks.
We fear we don't have time for more questions, so there's more, but I suggest we take them offline. Okay. So let's thank the speaker again. And